This question is from the 1986 exam AB Problem 1. It says, let f be the function defined by f of x equals 7 minus 15x plus 9x squared minus x cubed for all real numbers of x. Part A asked us to find the zeros of f. So, since this is a calculator active problem, we can plug this equation in for y1 and this equation in for y2 and find where they intersect. Now they intersect at x equals 1 and x equals 7. So, to prove that this is true, we plug it in the original equation like we did here and show that it equals 0. When x equals 1, the line is tangent to the y-axis because it ends up being positive on both sides of 1, so it just touches it twice, basically. Therefore, the zeros of f are x equals 1, 1, and 7, and you include 1 because the line just touches, it doesn't go through the x-axis. Okay, part B asks us to write an equation of the line tangent to the graph of x at x equals 2. So to do this, first we have to find the first derivative. First derivative is negative 3x squared plus 18x minus 15, and we plug in 2 for this to find what the slope is at 2, since first derivative tells us slope. After we do this, we plug 2 into the original equation to find the y value, so the point will be 2, 5. We then plug it in this slope-intercept form, and we get y minus 5 equals 9 times x minus 2. The equation was, the coordinates were 2, 5, and then the slope was 9. Part C of the problem asked us to find the x-coordinates of all points of inflection of f, and then to justify our answer. So we take the second derivative, which is negative 6x plus 18, and then we set it equal to 0. When x equals negative 3. So it equals 0 when x equals negative 3. The second derivative, when you go a little bit lower than 3, it's positive, and then when you're a little bit higher than 3, it's negative. So, f is concave up for all x less than 3, and f is concave down for all x greater than 3. Therefore, f has an inflection point when x equals 3 because it changes concavity.